Welcome to the second video in the series of high-speed trains. In the last video, we have discussed about the need to know about the high-speed rail systems, common characteristics of the high-speed rail systems, distinguishing features of the individual high-speed rail systems being operated in different countries, advantages of implementing high-speed rail systems, and the engineering challenges involved in setting up a high-speed rail system. If you have not seen the first video and you want to see that, then you can use the link given below. In this video, we will be focusing on the train designs of high-speed rail. While the first 4 parts of the lecture outline have been covered in the earlier video, this video will cover the remaining 3 parts. That is the basics of a high-speed train, the pioneer designs of the high-speed trains, and finally, the comparison between the 3 main design marvels. There are 4 subsystems in a high-speed train. First, the body structure of the coach. Body structure should be strong and lightweight. It should have smooth surface to reduce aerodynamic drag. Steel, stainless steel, aluminum alloys, or composite materials can be used for manufacturing a coach. However, aluminum alloys are mostly used presently, and extruded metal is used to reduce the weight of the train. The second subsystem is the coach bogie. It should be a lightweight bogie having excellent vibration control properties and less unsprung mass. It should be stable and should have less vibration in the vertical and horizontal planes. The third subsystem is the high power and lightweight propulsion systems. The fourth subsystem is the reliable braking system. Apart from above, there are subsystems related to passenger comfort like noise control, vibration control, handling pressure changes inside the coach, air conditioning, facilities for disabled, and catering facilities. And last but not least, there are safety systems. All of the above subsystems are state-of-the-art for high-speed trains, requiring years of research and development. Now we will see the pioneer original designs of high-speed trains. Japan, France, and Germany can be said to be pioneers in designing high-speed trains. All other countries have deployed derived versions of one of these 3 original or pioneer designs. For example, the high-speed trains running in Spain are the derived versions of design developed by France and Germany. Belgium, the UK, the Netherlands, and South Korea use the design of France. Likewise, Tiawan has Japanese design base. Russia has Germany design base. China has used all the 3 design bases, that is, Japan, France, and Germany. Nippon Sharyo, Hitachi, Kawasaki, Mitsubishi, Kinki Sharyo, and Tokyo Car Corp are the prominent rolling stock manufacturers in Japan manufacturing Shinkansen. Bombardier, now a part of Alstom, has supplied some versions of TGVs to France, AVEs to Spain, ICEs to Germany, ETRs to Italy, and CRH in China. Alstom has supplied some versions of TGV to France and AGV to Italy. Siemens has supplied advanced versions of ICE trains to Germany and their Velaro versions to Germany and France. CRRC in China has manufactured their advanced original versions of CRH. There are certain other rolling stock manufacturers also like CAF and Talgo in Spain, Transmash Holding in Russia, Ansaldo in Italy, Hyundai Rotem in South Korea, Stadler in Switzerland. Red color shows existing design options. If a country has to choose between the available design bases, these 3 are the main options. Asian manufacturers like CRRC and Hyundai are quickly catching up to the competition. Now we will discuss the Japanese Shinkansen trains, their genesis, evolution, and state-of-the-art. The genesis of the Shinkansen could be attributed to 2 men in Japan. During the 1950s, the existing quadruple narrow gauge track between Tokyo and Osaka, about 553 kilometers on the conventional Tokaido line, was reaching saturation. One proposal was to add 2 more narrow gauge tracks, supported by most of the Japanese national railways managers. But JNR chief Shinji Sogo had a different idea. He, supported by Hideo proposed to add a double standard gauge track. Shinji Sogo was president of Japanese National Railways in 1955. You can see monument of Shinji Sogo at the platform numbers 18 and 19 of Tokyo Station. Sogo devised a three-pronged strategy. Central to Sogo's strategy was the use of a loan from the World Bank, which was International Bank of Reconstruction and Development at that time, with a successful application for a $80 million loan, estimated to be no more than 15% of the cost of the line, in place. Commitment of Japanese government was ensured. Sogo devised this plan to make it almost impossible for the government to withdraw its support once given. Secondly, Sogo also kept down the declared maximum proposed speed at a relatively modest 200 km per hour and argued successfully that this was not a new line but an expansion of the existing T-Kid line. Thirdly, Sogo kept the estimated cost figures of the Tokaido Shinkansen deliberately low for fear that if they were too high, neither the Japanese government nor the World Bank would have supported the proposal. Also, it was in his mind that once JNR's total budget was approved by the National Legislature of Japan, the JNR president had discretionary authority over how to spend it. However, in 1963, when the budget diversion became a political issue, he resigned in 1963, taking full responsibility for the decision. It is also mentioned that in 1965, a year after the inaugural run of Shinkansen, Sogo was decorated by Emperor Hirohito with a Grand Cordon of the Order of the Sacred Treasure, an award recognizing his extraordinary service to Japan. Hideo Shima joined the Japanese government railways in 1925, where, as a rolling stock engineer, he designed steam locomotives. Shima was also involved in the design and development of the Class C62 and Class D60 to steam locomotives for express passenger trains and heavy-duty freight trains. It was during these initial years that he came up with the idea of distributed power multiple unit control systems. He became the head of the National Railways Rolling Stock Department in 1948. However, in 1951, a train fire at a station in Yokohama that killed more than 100 people led him to resign in the Japanese tradition of taking responsibility. He was asked by Shinji Sogo to come back and oversee the building of the first Shinkansen line in 1955. In 1958, Cabinet finally decided for standard gauge, construction period of 5 years, and at an estimated cost of 194.5 billion yen. Both Sogo and Shima went to USA for requesting the loan. The construction started in 1959. The opening was timed to coincide with the 1964 Summer Olympics in Tokyo, which had already brought international attention to the country. During the construction, the budget overflowed the limits and became double 380 billion yen. Sogo and Shima took responsibility and resigned. They did not attend the opening ceremony of Shinkansen in 1964. Yes, the origin of the high-speed trains lies in France when the efforts started during the early 1950s. When the French National Railway started to receive its new powerful CC70-100 electric locomotives from Alstom with a power rating of 3,450 kilowatts. In 1954, the CC70-121 locomotive hauling a full train with unmodified equipment achieved a record 243 km per hour during a test on standard gauge track. The next year, to specially tuned electric locomotives, the CC7107 and the prototype BB9004 broke previous speed records, reaching 320 km per hour and 331 km per hour respectively, again on standard track. For the first time, 300 km per hour was surpassed, allowing the idea of higher speed services to be developed and further engineering studies commenced. During the high-speed trials, dangerous hunting oscillation, the swaying of the bogies, which leads to dynamic instability and potential derailment, was discovered. This problem was solved by France 20 years later by using your dampers, which enabled safe running at high speeds today. The other issue was of research current harnessing at high speed by the pantographs that was also solved 20 years later by the Zebulon TGV's prototype, which was the first trial TGV. In 1955, The JNR researchers and engineers of Japan were present at the Lille's Electrotechnology Congress in France. They returned to Japan with a number of ideas and technologies. Major of them were use of alternating current for rail traction and use of international standard gauge for high-speed trains. In 1957, the engineers at the private Oda-Q Electric Railway in Greater Tokyo area launched the Oda-Q 3000 series say EMU. This EMU set a world record for narrow gauge trains at 145 km/h, giving the Oda-Q engineers confidence they could safely and reliably build even faster trains on standard gauge. Research and development of new technologies require extensive testing and trials before final deployment. All the countries having their original high-speed train designs have first developed high-speed test track in their countries. JNR used the Kamonomiya test track for testing and verification of construction standards, civil engineering structures, track, rolling stock, electric power supply and ATP systems. This test track was about 30 kilometers long and used from 1960 to 1964. Later, it was incorporated into the main line. The Zero Series Shinkansen, known as bullet trains in English, Danganreisha in Japanese, were built by Kawasaki Heavy Industries. It was a distributed power rolling stock. Overhead catenary was supplying 25,000 V. The catenary wire and suspension required new strengthened materials and designs with a high propagation velocity matching. Conventional trackside signaling systems were no longer of any use in securing safe operation at high speeds because Shinkansen crews could not respond quickly enough to the signal aspects. Hence, advanced in-cab signaling, automatic train control, and centralized train control have been used. Peculiar issues like high aerodynamic resistance, track adhesion, running stability, pantograph power collection, axle bearings, braking distance, and pressure waves when entering tunnels and passing at high speeds, noise generation were faced and were solved in subsequent designs of Shinkansen trains. There are 10 Shinkansen lines, 8 major and 2 small, and there are different operators operating in different Shinkansen. For example, in Tohoku Shinkansen JR, East operates using E2, E5, E6 and H5 series rolling stock. In Tokaido Shinkansen JR Central operates using N700 series rolling stock. This is the list of the types of rolling stock presently running in Shinkansen services. The 2 latest versions, N700, introduced in 2007, and the E5, introduced in 2011, will be explained in detail. N700 was a game changer in Shinkansen designs due to first use of active suspension and tilting technology. It also uses a new ATC system. N700 is the first high-speed rolling stock of Japan with a body inclining system. Passenger comfort was improved by installing an innovative high-performance semi-active suspension system in all cars. Semi-active suspension to suppress vibration by changing the damping capacity of the lateral oil dampers has been applied. Longitudinal vibration has been suppressed by employing a combination of smooth braking through the use of the new ATC system and reducing the number of accelerations and decelerations necessary at curves through the use of the body inclining system. In the E5 series, the standard train length is 10 cars and the formation is 8 motor coaches and 2 trailer coaches. The train length is 250 meters. The maximum operating speed is 320 km/h. Complete aluminum body coaches are used. The traction system uses Metricton 207 AC traction motors with a rated power of 300 kilowatts. The total power output is 9,960 kilowatts. Single-phase overhead supply is interfaced to the traction motors with power converters. Traction transformers and traction motors represent the high power systems based on electromagnetics. Advanced design for electromagnetic and electromechanical power transfer, materials, and cooling are the key design aspects. Traction system. The energy efficiency of the traction system was improved by adopting a higher capacity drive circuit together with the use of silicon carbide devices and highly efficient IMs. The capacity of the traction system is sufficient to drive the 300 kilowatts main motors needed to achieve the maximum speed of the E5 Shinkansen. The E5 series trains feature a long nose design to minimize micropressure waves in tunnels, bogie covers, and full intercar covers to reduce air resistance, along with a low noise pantograph. The E5 series has introduced active suspension, a computer-controlled system to suppress vibrations, offering a significant advancement over traditional methods. Unlike the semi-active suspension used in earlier models, which relied on oil dampers and had inferior vibration damping capabilities, the active suspension in the E5 series excels at reducing lateral vibrations. Vertical vibrations are managed effectively using air springs. Additionally, a car body tilting mechanism, also utilizing air springs, enhances passenger comfort when navigating curves. Now we will move over to the HSR train designs of TGV France. The TGV, while serving a similar high-speed rail purpose as Japan's Shinkansen, adopts a distinct design approach. TGVs feature articulated sets of 8 unpowered coaches connected by Jacobs bogies, which support adjacent carriages. Trains can be extended by coupling to TGVs using concealed couplers in the power car's noses. This articulated configuration enhances safety during derailments, reducing the risk of trains splitting and jackknifing compared to conventional designs. However, splitting carriage sets is challenging, requiring specialized depot equipment, though power cars can be detached using standard uncoupling methods. All TGVs are equipped with 2 power cars, a design choice by SNCF to minimize electrical equipment compared to electric multiple units. TGVs are at least bicurrent, capable of operating on 25 kV 50 Hz AC and 1.5 kV DC for interoperability. When transitioning between different voltage zones, drivers are prompted by marker boards to deactivate power, lower the pantographs, adjust a switch for the correct system, and raise the pantographs. Pantograph selection and height adjustment occur automatically based on the driver's voltage system choice. For routes to Germany, Switzerland, Belgium, and the Netherlands, tricurrent or quadricurrent TGVs are used to accommodate additional voltage systems. TGV Southeast was the first TGV to be introduced. The Atlantic TGV rolling stock marks significant technical progress in terms of performance, 8,800 kilowatts power, as opposed to 6,450 kilowatts for the Southeast TGV. Capacity, 485 seats as opposed to 368 seats, and comfort, as confirmed by runs at 300 km per hour and beyond. TGV Duplex and TGV POS are double-decker trains. This is TGV Southeast. The Atlantic TGV rolling stock marks significant technical progress in terms of performance. It uses 10 intermediate coaches between the 2 powerheads. All Atlantic TGVs are at least bicurrent, can operate at 25 kV 50 Hz AC and at 1.5 kV DC. TGVs have 2 pairs of pantographs, 2 for AC use and 2 for DC. Unlike the TGV, which was developed in collaboration between Alstom and SNCF, the AGV was developed wholly at Alstom's expense. The AGV was promoted in 2002 as a complementary high-speed train to the TGV Duplex double-decker, offering higher speeds for less busy train paths. Distributed power with permanent magnet traction motors was used in AGV. Now we will move on to Germany's ICE trains. The first series of ICE trains operated by Deutsche Bahn is notably longer than the TGV, typically featuring 11 to 13 intermediate coaches. These trains utilize solid monoblock wheels and air suspension on their axles. Each of the 2 power units is equipped with powered bogies, driven by 2 3-phase asynchronous motors, delivering a total rated power of 4.2 megawatts. The ICE-1 and ICE-2, both power-head-driven, have a loading gauge that exceeds UIC recommendations. The braking system is particularly advanced, combining an electrical regenerative brake, mechanical disc brakes, and an eddy current rail brake. Compared to the French TGV, the ICE1 offers greater comfort and more spacious interiors, surpassing even the Shinkansen in these aspects. Additionally, the number of coaches can be adjusted to meet specific operational needs. ICE3 were built as electric multiple units or with distributed power rolling stock. Simultaneously with the ICE3, Siemens developed trains with tilting technology, the class 411 7 cars and 415 5 cars, ICET electric multiple units. ICE3 built by Siemens Velaro is a potential design-based candidate for emerging railway systems. Now we will delve into the evolution of high-speed rail in China. In 1997, decision was taken to introduce HSR in China. Trials were done onto indigenous designs on a specially built test track. Up to 2003, R&D of this field in China was based on China's own knowledge and skill. But the policy changed after 2003. As it was revealed to be too slow to catch up with the national fast-growing economy, the government decided to change its own method of realizing HSR based on its own internal development to the introduction of technologies from developed countries. Chinese change of ways of realizing high-speed railways in 2003 was very clever to catch up with developed countries and to become world best high-speed railway holder. The main technical imports include coaches, signaling transport management, and ballastless tracks. For coach technology, 4 base designs were selected. The Swedish Bombardier Regina, which was manifested into the CRH-1 design of China. The JR East Haiti E2-1000, built by Kawasaki Heavy Industries, resulted in the CRH-2 design of China. The German ICE3, built by Siemens, resulted in CRH-3. The Alstom Pendolino resulted in CRH-5. CRH-1 and CRH-5 were the basis for developing medium-speed train sets. CRH-2 and CRH-3 were the basis for developing high-speed train sets of Chinese origin, the CRH-380 series. Their method involved modifying the designs to suit Chinese needs in areas such as body width and interior fittings. These are the images of medium-speed CRH-1 and CRH-5 trains, high-speed CRH-3 and CRH-2 as well. After manifesting CRH-1, CRH-2, CRH-3 and CRH-5 trains in 2007, they moved their trajectory into a higher orbit to become one of the world leader in HSR train designs. The Chinese railroad engineers studied data in the public domain. They introduced principal technologies from foreign nations and nurtured their own railway industry. Technologies were managed centrally using the required test tracks, and the CRH-380 series high-speed trains were developed by China itself. CRH-380 has been in operation since 2010. Its maximum possible speed is 380 km per hour. Now we will discuss some comparative figures of the 3 main design bases for high-speed trains that are Shinkansen E5 Siemens Velaro and Alstom's AGV. Before going into the technical details of the 3 designs, we will go into the basic design philosophies of the Japanese Shinkansen and the French TGV. Shinkansen means new main line. It serves as a huge backbone from which smaller branches, not all high-speed lines, branch out to connect the entire country. It passes through a series of densely populated townships. It has frequent stops around 50 kilometers apart. The hilly terrain of Japan requires more curves and tunnels. Minimum curve radius is 2,500 meters, and the rolling stock has long noses and small pantographs. They can accommodate 3 to 4 passengers per meter of the train. On the other hand, the France TGV lines connect the corners of the country to the capital city, Paris. Lines are not so densely populated, and the stoppages are also not frequent. They can accommodate to 2-3 passengers per meter of train. Minimum curve radius is 4,000 meters. There are no mountain terrains to traverse in France, so no tunnels are required to be cut through. Smaller noses that save train length and bigger pantographs are used, which are safer. France TGV has a lesser passenger capacity, but is more comfortable and spacious, and has a higher critical speed due to stiffer train sets having Jaco bogies. While Shinkansen trains tend to become unstable around 420 km per hour, TGV holds the world record for the fastest wheeled train, 574 km per hour. There have been certain debates on the choice of the power head-based high-speed trains like the original TGVs or the distributed power-based rolling stocks like the Shinkansen. There are numerous advantages of distributed power rolling stock over concentrated power heads. They have smaller axle load. They have high acceleration and deceleration due to a large number of driving axles. There is more cabin space as there are no locomotives. Since the number of motorized axles is more, they have the ability to utilize the energy of regenerative braking efficiently. The distributed power multiple units have driver desks at both ends, so that there is no need for power reversals at the end of one side of the journey. With 40 to 100% powering of axles, the performance of the train is independent of the train length. Development of AC traction motors and traction converters in the 1990s led to the choice of a distributed power system as a preferred choice. As you can see that almost all the countries implementing high-speed rail after 2000 have used distributed power rolling stock. Hence, the three preferred distributed power-based design options are E5, Shinkansen, AGV, Alstom, and ICE, Siemens Valero. A comparison of some important design features is given in the table. As we can see that the Japanese Shinkansen has the largest car width of 3,360 mm. E5 carries the highest number of passengers, and the axle load of Shinkansen E5 is the lowest amongst the three design options. Alstom AGV is the most spacious. Alstom AGV has advanced permanent magnetic-sighted synchronous traction motors. To summarize the comparison, we can say that each and every design above is a design marvel in its own way. They have their own distinctive features and advantages. Though they can be compared on various parameters like axle load, maximum operating speed, passenger carrying capacity, hourly passenger transport capacity, cost implications, energy efficiency, technical parameters like power per passenger, and physical parameters like weight per passenger. One has to decide according to their requirements, criteria, resources, and constraints. So friends, we have now completed the lecture. I hope that you have enjoyed the lecture. Thanks a lot for your patience. These are the main sources used for making this lecture and for your future readings. Please like the video and subscribe the channel if you want more content like this. Thanks again and goodbye for now.